Hello my dear students, I am Dr. Sarika Kalra, Associate Professor from Electrical Engineering Department and Ajay Kumar Garg Engineering College. Today I am taking the second lecture of Electrical Machine 1. In that previous lecture I have discussed about the because in Electrical Machine 1 we are going to study the transformer and the DC machine. So, I have first taking the transformer. So, in first lecture I am discuss the what are the magnetic circuits and what are the laws which is associated with the magnetic circuits. And in the previous lecture I have also discussed the how this DC supply, where the magnetic circuit with the DC supply and the magnetic circuit with the AC supply. So, in the last lecture also we have seen that when you apply the AC voltage into the magnetic circuit, the flux as you apply the voltage, the flux will produced and it is confined with the core, and this flux value is remain constant. It is depend upon the voltage and the frequency that we have seen already. So, so the requirement of the current produce that flux is very small, that already we have seen in the last lecture. Like if you see the in last lecture we have seen the BH curve. We have already got this. If the supply voltage is Vn, the phi maximum that is produced in the core is equal to the V1 4.44 Fn1. Okay. So, this phi max is constant and it is depend upon the voltage and the frequency. The voltage is, the supply voltage is constant and the frequency is also constant, so the phi maximum is constant. So, if this is BH curve, which is between the flux, or you can say flux density, and H, or you can say the I, that is magnetizing current. So, according to this BH curve, the current value corresponding to this phi max is, suppose this is I1. Now, if you see, if you take the another material which have the higher permeability, suppose this is material 1 and this is material 2. So, the material 2 has the higher permeability than material 1, that is mu 2, that means mu 2 is greater than mu 1, and the mu is increasing, the requirement of the current for the same flux will reduces, and this current is called the magnetizing current. So, this is the concept we have discussed about the magnetizing current, how the magnetizing current come into the picture. So, when you apply the voltage, the flux will produced, and that flux is constant, at which is depend upon the voltage and the frequency. So, the requirement of the flux, I mean the requirement of the current to produce that much flux is very small, because it depends upon the, if you take the higher better material, the requirement of the current will become smaller and smaller, and if the permeability tends to become infinite, the current, the magnetizing current vanishing to the 0 value. Okay. So, this already we have discussed in the last lecture. So, now we will start the transformer. In this lecture, first I will going to discuss the transformer applications. What are the, why we going to study this transformer, then the ideal transformer assumptions, the phasor diagram of the ideal transformer, the equivalent circuit of the ideal transformer, then we do some numerical which is related to this ideal transformer. Okay. So, transformer is a static device which transform the electrical energy from one electrical circuit to the another electrical circuit through a medium of magnetic field without changing the frequency, and it is based on the principle of electromagnetic mutual induction. So, the basic function of transformer is to change the level of voltage from higher to level, or you can say lower to higher. Okay. So, these transformer are used in the power transmission line, where the generation is suppose the 400 volt, and you have to transmit that volt to the load end side. So, you transfer this voltage from through a transformer, so that you can increase the level of voltage and transmit it at the load side. So, you connect another transformer to reduce the level of voltage, because when you transmit a power with the high voltage, the losses will be less. Okay. Second, the application is the transformer is the impedance matching for the maximum power transfer. Third, you can say that the transformer is used to isolate the two electrical circuit, because in transformer there is a, if you consider two winding transformer, there is a no electrical connection between that. The two winding is connected through a medium of magnetic circuit. Okay. So, now I am taking the ideal transformer. What do you mean by this ideal? Ideal is, I mean, perfect. Okay. So, but nothing is ideal in this scenario. Okay. So, first I have considered the ideal transformer, so that the equation become easier, and after that I have inculcate the reality into the transformer, so that you see the practicality of the transformer. Okay. So, in ideal transformer, some assumption I have to take, right. Okay. Suppose this is the so here you apply the voltage, that is sinusoidal voltage. This is switch, and this is suppose the load is there. Now, in ideal transformer, first you assume that the winding resistance is 0. I am taking the another slide, assumptions. So, first I assuming that winding resistance of both the winding are 0, sorry. Second assumption you are taking, like there is a no leakage flux. No leakage flux means all the flux which is produced by the source voltage is confined within the core. Like if you see, when you apply the voltage, the flux is producing, and it is the time varying flux, sorry. So, this flux is the produced by this flux voltage is all flux is confined within the core. There is no leakage flux in the this winding, or you can say this winding. So, all flux is linked with the, this is called the mutual flux, which is linked with the primary winding as well as the secondary winding. Third assumption I have taken, like the magnetizing current is very small. That means you have taken the very good material, so that the magnetizing current is very small, or you can say it is vanishingly small. Okay. Or tends to 0, you can say. If you take as a mu, I mean very good material. So, I have taken very small ion. Fourth assumption, that you assume that there is a no core losses. Okay. So, these are the 4 assumptions we have taken to study the ideal transformer, because in practical this can't be happen. So, when we take the practical transformer, one by one I have inculcate these all 4 into the practical transformer to become a real transformer. Okay. So, if you suppose connect here emitter, suppose this is the no load, I mean the S is not connected, so the load is not connected. So, Vn, when you connect this Vn, the current will start flowing, small current. If there is a no resistance, this is purely inducting, that means the current is lagging with the voltage, okay, and the flux is produced due to this current. So, the flux is always in same phase with the current, okay. So, and this current is very small. Suppose the number of turn in the primary is N1 and the secondary is N2. So, the MMF produced by this current is NIM, N1 IM. So, IM is, if it is very small, the MMF is, the requirement of MMF is small, and that will produce the your flux. Okay. So, these are the four assumptions we have to take to study the ideal transformer. Now, we see that when you apply this voltage V1, you have seen that the changing magnetic field is produced, because this voltage is the sinusoidal voltage and the current is, of course, is a sinusoidal if the voltage is sinusoidal. So, the flux is also a changing magnetic field. Okay. So, with this changing magnetic field, according to the Faraday's law, the EMF is induced in this winding. Okay. Suppose the EMF is like this E1, and the polarity of this E1 in such a way that it opposes the very cause of this production of the flux. Okay. So, the polarity in such a way so that it opposes the flux. Okay. So, if you take phi m is equal to, sorry, for reference for taking reference flux phi is equal to phi m sin omega t. Okay. So, EMF induced in the primary coil is equal to n d phi by dt, and negative sign represent the, according to the Lenz's law, it is opposes the cause. Okay. Put this phi value in equation 1. So, it can be written as, there is omega also, n omega phi m sin So, in this equation this represent the maximum value of EMF induced. Okay. So, E max become this n omega phi m and in case of this primary side I have taken the number of 10 turns is n1. So, here it is n1. And omega is of course 2 pi f phi m, where omega is equal to 2 pi f. Okay. This is E max. So, the RMS value of voltage represented by suppose E1, this is RMS, the E max by root 2. So, it become N1 phi m by root 2. So, it become 4.44 f phi max N1. This is E1, the RMS value of EMF induced in the primary coil. So, how the transformer function will takes place when you apply the voltage here, very small current will set up because of, you assume that it is ideal because of you have taken the very high permeability material. So, the requirement of flux is set up is constant. So, the requirement of this magnetizing current is very small, and this changing flux is kind of change, I mean this flux is a changing flux. So, EMF is induced in the this winding, and this flux is also linked with the secondary winding. So, according to the Faraday's law, EMF is induced in the secondary winding also, and suppose it is E2, and you have considered in this case the switch is open. So, it is a no load condition, and so the V2 is equal to the, suppose the load voltage is V2, I mean this, so V2 is equal to E2 because there is a no load and the no current is there. So, V2 is equal to E2, and in this case you assume that there is, in ideal transformer there is a no resistance. So, it is kind of purely inductive. So, this current is always 90 degree behind this voltage, or in other way you can see that according to this flux is this, you have taken a reference voltage. So, this equation, the equation A and equation B express that the voltage is the E1 voltage is lagging with the flux, because here the term is sin omega t, here that sin omega t minus pi by 2. Okay. So, transformer action takes place, this voltage V1 is applied, changing magnetic field is set up, E1 is induced, and this E1 is, and this flux is linked with the secondary winding. So, according to Faraday law, E2 is also induced in the secondary winding. Okay. So, the same flux is linked with the, at secondary side, suppose same flux is linked with the secondary winding. So, E2 can be represented as, and in secondary winding there is an N2 number of turn. So, according to Faraday's law it become like this, so negative sign. So, similarly this can be also written as so E max value is this, E2 max value. So, E2 max is equal to, you can say, the N2 omega phi m. Okay. So, E2 RMS has become this N2 omega phi m divided by root. So, it become 2 pi f divided by root 2 N2 phi m. So, it become 4.44 f phi m N2. This is E2 RMS voltage induced in the secondary coil. Okay. That means the E1 is EMF induced, the RMS value of EMF induced in the primary coil is this much, that is suppose D, and this is suppose E. So, if you taken this E1, and if in this case you have seen that E1 is N1 omega phi m sin omega t minus pi by 2, and E2 is also sin omega t minus pi by 2. That means E1 and E2 both are lagging with the flux phi m, flux phi, if you take in phi m as a reference flux. Okay. So, if you divide D equation with the E. So, you will get E1 upon E2 is equal to 4.44 F phi m N1 divided by 4.44 F phi m N2, and this can be written as E1 by E2 is equal to N1 by N2. Okay. So, this is how the transformer action takes place. So, E2 will be generated according to the number of turns which is present in the secondary winding. So, according to the number of turns, we can change the level of voltage from primary to secondary. Okay. So, E2 will get depending upon the number of turns. If you know the E1, so you will find the E2, and it is depend upon the number of turns in the primary and the secondary. Okay. So, this is how this transformer action takes place. Now, we see the phasor diagram at no load. Phasor diagram of ideal transformer So, in this case you have seen that if you see the diagram, you have to draw the phasor diagram at no load. That means you haven't switch, this switch is S is open, there is no current in the this winding, right. So, you are drawing the phasor diagram for ideal transformer. You have assumed this assumptions like winding has no resistance, no leakage flux, that means all flux is confined within the core. Third is the magnetizing current is very small, that is vanishingly 0, because you have taken the good material of core. And third is there is a no core loss in the material. Okay. So, for that you have taken the reference flux phi m sin omega t. So, to draw the phasor diagram, first you have take the reference flux. Suppose this is phi. Okay. And in this case, you see in this diagram, when you apply this voltage, the flux is fixed within the core, and it depends upon the voltage and the frequency. Okay. Now, and obviously this is a sinusoidal phase, single phase, the frequency f, single phase, sinusoidal voltage. So, obviously this current is also sinusoidal and the flux is sinusoidal. That is why I have taken phi m sin omega t. But you assume that there is no winding resistance, so it is an inductive kind of. So, the current is lagging with the voltage by a 90 degree. Okay. And this current is also responsible to produce, to produce the MMF. So, it is in the flux is in same phase with the current. Obviously, it is very small. So, you just taken like, I am just taking the another color. Okay. So, this is I m. Now, when you derive the voltage E1 and E2, E1 is induced due to the Faraday's law when you apply the voltage, and it is 4.4, it is coming omega sin omega t minus pi by 2. That means it is lagging with the flux by a 90°. I am just taking another. Now you can draw E2. E2 is also the same phase with the E1 because it also term has sin omega t minus pi by 2, and the length of the E1 and E2 depend upon the number of turns. So, suppose the E2 the N2 is less than the N1. So, E2 is less than E1. So, I have taken length less than the E1. Okay. And obviously, in this circuit you see that the polarity of the E1 is become like this point will become positive and this is become positive, this is become according to the Lenz's law, because E1 is produced in such a way so that it opposes the cause of production. Okay. So, and this must satisfy the KVL also. So, V1 in this case V1 must be equal to the minus E1 in this case. Okay. That means E1 Rn V1 is like this and it is equal to minus E1. Okay. I just draw Im again because the yellow color is not very dark. I just erase this. Okay. So, this is the phasor diagram of transformer at no load, of ideal transformer at no load, where the Im is very small and negligible. So, this is the phasor diagram of ideal transformer at no load, where there is no load connected at the secondary side. Okay. The switch S is, at this case switch S is open. Okay. So, at this case when you take the phi is the reference value, the current is sinusoidal, the flux is sinusoidal. You assume that flux is, because obviously the voltage is, the supply voltage is sinusoidal, the current is sinusoidal and the flux is also sinusoidal. So, flux, the current is the flux is safe phase with the magnetizing current. Okay. And we have already seen that the E1 and E2 voltage produced by the transformer action is always lagging with the flux by a 90°, that you have seen from this equation. Like the sin omega t, the E1 has the sin omega t minus pi by 2 and E2 also involve this sin omega t minus pi by 2. That means the flux is, the E1 E2 is lagging with the pi. And what about this V1? If you see the diagram, this transformer diagram, this polarity E1 is, this become positive, this become negative because of the Lenz's law. It must produce in such a way so that it opposes the cause of production, and it must satisfy the KVL. So, V1 must be equal to the minus E1. So, this is the phasor diagram at no load. Okay. Now, we consider the phasor diagram when this switch is become, when there is a load, Z2 load is connected, this is voltage across the this winding, Z2 load is connected, and when switch S is closed. As moment the switch S is closed, the current will start flowing. Suppose this is current I2. Okay. When the current is start flowing, suppose I have assumed the direction of the current is in this direction. There is two possibility to the direction of current. Either the polarity of this voltage is like this, or this is minus or this is positive plus. How will it take this plus or minus or plus? It will depend upon the Lenz's law. Like, as the moment the switch S is closed, the I2 will flow through the secondary coil, through the load to the secondary coil, and the direction of I2 in such a way, and this I2 is produce its own MMF, because there is a number of turn is N2. So, N2 I2 MMF produced at loading condition become N2 I2, and that MMF will create a flux. Okay. Suppose the direction of the flux in such a way so that it aids the magnetizing flux, the useful flux, but the useful flux is constant because your voltage is constant, because you have to satisfy this the KVL. So, the voltage the flux is constant, okay, because your supply voltage is constant. So, that MMF has to be nullified, okay, so that the core only maintain the flux the phi m, the magnetizing flux. Okay. So, as the moment the switch is closed, the I2 will start flowing. Suppose the direction of I2 is this way. So, the flux is produced in this direction, and if the current is the direction, you see that the current direction is like this, the flux is produced in opposite direction, and if the current of direction is the current of direction is like this. So, the magnetic field produced like in this direction. Okay. So, when the magnetic field is the MMF, N2 I2 will produce the flux which is in same direction with the phi m, it will aid the flux. Okay. So, the flux, the direction of current must be like in such a way, so that this become polarity, this is positive and this is negative. So, we can take this positive and this is negative. Okay. Now, as the switch is on, the MMF N2 I2 will produce, and this N2 I2 have to nullify. So, the source will draw the extra current which is equal to the I2, that is I2 dash, so that it will nullify the effect of N2 I2. Okay. So, the MMF produced by this I2 dash is N1 I2 dash, and this MMF N1 I2 dash must be equal to N2 I2, so that all the flux which is produced by the N2 I2 must be nullified with the flux produced by this N1 I2 dash. Okay. So, that flux must be nullified. So, this I2 current is called the load component, because when the transformer is loaded, the I2 current will fill, and according to this I2 current, reflecting current will extract from the source, that is I2 dash, so that the core will maintain the flux, the magnetizing flux, maintain the magnetizing flux. So, this is how, like, if you see that, now we see the loading effect. So, if as the switch is on, I just draw again. As this switch is on, suppose this has an N1 number of turn, V1 is the supply, N2 number of turn, the EMF induced in this E1, here the EMF induced is E2, and this is suppose the load impedance, the voltage across this load impedance is V2, okay, and the flux is phi m. When the switch is open, the flux maintained by this core is phi m. Okay. As your switch is on, the current I2 will flow, and that will create, suppose, MMF as okay. So, that MMF will create a problem, because flux due to this MMF will add in this. So, because due this the supply voltage is constant, so phi m is constant, and it remain constant either the switch is on or off. Okay. So, that means this N2 I2 must be compensated. So, as the I2 will flow, this transformer will extract more current from the source, so that the effect of this N2 I2 will nullify. So, suppose the current which is flowing in the primary is I2 dash. So, MMF produced by I2 dash is equal to N1 I2 dash, because the N1, the number of turns in the primary side is N1. So, and at no load condition, it also draw the IM current, already draw the IM current, that is magnetizing current, that is very small, that is responsible to produce the flux phi m. So, the total MMF in primary side this becomes N1 Im plus I sorry N1 I2 dash, and the MMF produced in the secondary side is equal to N2 I2. So, total MMF in the core is I have taken negative because if the direction of this MMF is like this, and so I mean if the direction of the N2 I2 is like this, so N1 I2 dash must be in this direction, must be in this direction. So that the F this become 0. So the MMF remain is N1 I1, and due to this MMF phi m will produce. So either the switch is on or off, the flux remain the same in the core, and flux with the MMF produced by the flux is N1 Im. Okay. So this is the loading effect. So that N1 I2 dash must be equal to N2 I2, and in the direction of this MMF will be opposite. So that must be satisfied. N1 I2 dash is equal to I2 N2. That means I2 dash is equal to I2 N2 by N1. Okay, this is the loading effect, you can say, or this is the loading component. So now when the load is connected, switch is closed, the total current drawn from the supply side become, so the I1 become in the primary side, there is a current Im, and due to this loading this is I2 dash. So the total current in primary side is this much. Okay. So this is the total current which is flowing in the primary side when the switch S is closed. Okay. And this Im is the magnetizing current, which is very small in comparison, it is very small in case of ideal transformer, it is kind of, you can say it is 0. So and I2 dash is the load component, and it is equal to the I2 N2 by N1. Okay. So now we see the phasor diagram of the ideal transformer at load condition. Sorry. Sorry, it's pen is not working, I think. Ideal transformer at load. Now suppose this is the reference flux, we already have assumed that this flux this is Im, which is in same phase with the flux, okay, and the EMF and EMF E1 and E2 which is produced by the through a transformer action, it is lagging with the flux phi with the 90 degree. Suppose this is E1 and this is E2. I have taken E2, sorry, this is E1. So, if the number of turns N2 is less than E1, so you have taken this E2 is like this in same phase with the E1. Now, as the switch is closed, in this case as the switch is closed, the I2 will start flowing, and suppose the impedance is Z2. So, the power factor is suppose is theta 2. Okay. And obviously, it has no winding resistance, it is an ideal transformer. So, E2 is equal to the V2. So, this is V2 suppose. So, suppose the impedance, the load impedance is Z2. So, the power factor is suppose theta 2 . So, the current is suppose I2, this is lagging with the voltage, it is an inductive kind of load you have assumed. So, the theta 2 is lagging with the voltage E2. Now, as we have seen that as the switch is closed, the I2 current is flowing in the primary in the secondary winding, and to nullify this I2 current, the same current will produce in the primary side, so that it will create a same MMF, like if this I2 will create N2 I2. So, the MMF in the primary side will create I2 dash into N1, so that it will nullify the effect of load. We can draw the equal and opposite in the primary side. Suppose it is I2 dash. Okay. Now, in the primary side, now two current is flowing. One is Im magnetizing current, other is the load current. Okay. Magnetizing current is, you can say, it's it is used to required to produce a flux which is confined within the core, that is useful flux, and I2 dash is the effect of due to the loading effect. So, the total current which is flowing in the primary is phasor sum of I2 dash plus Im. So, if it is Im, we can combine this and this become I1. That means I1 is the phasor sum of I2 dash plus IM. Okay. And this is the case, this is the phasor diagram of ideal transformer at, sorry, it is not no load, it is a load, I am sorry, at load, at lagging load, because you have taken the Z2 kind of inductive. So, it's you have taken theta 2, I mean the current is lagging with the voltage. So, it is a kind of lagging load. Okay. So, this is the phasor diagram of ideal transformer at lagging load. Okay. Now, we will discuss, and also you can draw the phasor diagram at leading load also. In that case, you just take the I2 which is leading with the voltage V2 and then phasor sum of Im and I2 dash. Okay, you can draw this also, and this is the I1 current, and this equation must satisfy like N2 I2 must be equal to I2 dash N1, so that flux phi m remains in core because it is constant and depend upon the supply voltage. And frequency. I have seen, we will see the phasor diagram of ideal transformer at leading power factor, when your load is kind of leading in nature. That means there the current is leading with the voltage. Okay. So, similarly in case of lagging, you just first draw the flux and the current is very small, that is Im, the magnetizing current which is in same, the flux in same phase with the magnetizing current. Then you just draw the E1 and E2, and E2 must be equal to V2 in case of ideal transformer. Okay. Now, suppose this, here you will see that as the switch is closed, suppose this Z2 is in, the load is, it is in capacitive nature. That means the current is leading with the voltage. So, now the current is, suppose I2 this is I2 and it is leading with the voltage by angle of theta 2. Now, as you can see, as the loading effect, the current, the primary current will draw the same amount of current, I mean produce the same amount of MMF which is produced by this I2 current. That means I2 N2 is equal to, again I am saying this I2 N2 must be equal to I2 dash N1, and I2 depend upon the load, which kind of load is there. So, according to that, the primary will draw the more current from the source, so that it will satisfy this equation. Okay. So that the flux is phi m, which is produced by the current, magnetizing current, it remain constant within the core. Okay. And in the phasor diagram you have seen that V1 is equal to minus V1. So, you can draw like this. Now, as the I2 current will flow, this the equal and opposite current will flow in the primary, that is I2 dash. Okay. Now, phasor sum of this Im and I2 dash will become this I1. Okay, and this will depend upon the degree of this theta 2. Okay, how the theta 2 is. Like if I2 is close to this V2, this I2 dash will more to this side and I will become lagging with this voltage V. Similarly, I1 is equal to I2 dash plus Im. So, now this is the total current which is flowing in the primary side. So, this is the current when switch is S is open, and this both current is are present when the switch is S is closed. So, this I2 dash become a loading component. It is called a loading component. Okay. So, this is in this lecture we have seen that how this ideal transformer is, what is the function of the transformer, what is the application of transformer, and if you consider the ideal transformer, what are the assumptions you have taken, how this behave when it is at no load, and how the phasor diagram will draw at no load. After that you have seen that when the transformer become loaded, a loading current is there, the MMF produced by this loading current which must be nullify the effect of the N1 I2 dash N1, so that the core maintain the flux phi m constant. Okay. So, in the next class we will see how the practical transformer behave. So, in practical transformer, the assumption which I have taken in the ideal transformer, these we will inculcate in the practical transformer one by one. Okay. So, thank you, and if you have any query you can contact me on my email ID, that is kalrasarika@akgec.ac.in. Thank you all.